Hello. We are going to talk about a two-dimensional problem today. So we have a rectangular plate. This side is A and this side is B. And we want to study the oscillation of which is 90 degrees to the surface of the plate. So if you look at it in a Cartesian coordinate system, this side can be x-axis and this side can be y-axis. So this is A0 coordinate, this is 0, 0, and this is 0, B coordinate, and this is A, comma, B coordinate. So so it has you can specify boundary conditions on these four sides, these four edges. The z-axis is coming out. So here the oscillation is basically displacement of any particle. Say this is at xy. So if you look at this particle, it's going up and down, and so it will be z as a function xy at certain time t. So this would be the displacement. And in one dimension you had a tension. Here it will be surface tension, which would be the force that we will have, that will be the restoring force for the motion. So when we'll not work it out, but you can derive this. So if you look at a neighborhood of xy and look at the forces, you can derive that d square z, which is a function of x and y, dx square. So it's like depending on the x direction versus depending on the y direction, d square z dy square, that will be 1 over v square d square z dt square. So this is the acceleration. The v is a classical wave equation. It's called two-dimensional classical wave equation. You could use another symbol for this, and we have used symbol psi for it before. So we could say this is d square psi dx square, d square psi dy square, 1 over v square d square psi dt square. The psi just stands for the displacement variable, and this is a general way of talking about other things that may be not just rectangular plate, but some other things which behave in a similar way, where the displacement variables have a different physical meaning. So we will use this notation. That's the notation in the book also. So let's see. So this is a local in the neighborhood of xy. This is the classical wave equation. And we will, just like in one dimension, the solution, if you want to solve this, it depends on what the boundary conditions are. So boundary conditions here, there will be, let's see, there will be 4 different bounding, one along this edge, one along that edge. So we can just write them down as psi of say if I'm on the this edge along the x-axis, then I'll have x varies between 0 and a, but y is 0, and at all time this is 0. So that's the x-axis, and x is between 0, and then we have that's one boundary condition. The second one will be along the y-axis. So x will be 0, x is 0, and y can be any, and the y is between 0 and b. This edge will be psi, where x is a, but y varies between 0 and b. So let's call that 4, and let's call this 3, and put 2 here. The parallel to the x-axis over there will be psi x, y equals to b, t equal to 0. So these are 4 boundary conditions. So we want to solve this equation subject to these boundary conditions. So if you remember, in when we solve one-dimensional problem where you don't have this part, the smallest oscillation is that. So if you have 2 dimension, you should get something like that and something like that, and so there will be kind of a one peak like thing in the middle. Should get something like this because we expect equations to behave consistently. Okay, so if you remember how we did this, this was done by separation of variable technique. So this one, same way, the way we're going to solve is look for normal modes, by a product solution. So we'll have a psi which is of x, y, and t. It's going to be actually product of a function just depends on space, and for a function that depends on time. Furthermore, we can actually separate out even more. So let's see if I some f of x and y, h of t. So this is the space part, and this is the time part. So this will have the frequency as we will see. Let's see. So we put this in here, and you can see that you will get d square f h d square f dx square plus d square f dy square. So h of t kind of factors out here, and on the other side f of xy factors out, and this becomes d square h dt square. I can divide by f h, so f times h, and divide by f times h. So h cancels out here, and f cancels out here. So if you look at this part and this part, so on the left side we have purely just a function of x and y. This is function of x, y, and this is a function of t. And there x, y, and t are independent variables, so it will be equal only if both sides equal to the same constant, some constant, which you can we will denote now by minus k square. Okay, so we'll just call it minus k square. It's not important that it's minus or plus, but later on it will be important. But this is right now just some negative number. Well, so let's look at what this will do, and then this with that will do. So the time part looks like as follows. You can have h on the other side and bring v square on the other side. So this becomes d square h dt square equals to minus k v square h. Now this is a simple harmonic oscillator problem, and that's why this negative important, because we want because we want oscillatory solution. We want oscillatory solution. So this h of t, you can see, is some a cosine kVt plus some phi, and this is that omega. We don't know what the omega will be, allowed omega. Don't know allowed omega yet. We'll find that when in the due course. So the other one with this with that is an equation which looks like d square f dx square d square f dy square equals to minus k square f. Now we can seek another product solution. So now we can say, how about we say f xy is is a, maybe you have a maybe let's call it pick a p of x and q of y. All right, so when we do that and let's see, so over here it's going to be q d square p dx square plus p d square q dy square, and this is ordinary derivatives, minus k square pq, and if you divide by pq both sides, so this pq cancels out. Over here it becomes 1 over p d square p dx square plus 1 over q d square q dy square equals minus k square. We can put this on this side. Then we get. Let me move this out of the way. So we have a 1 over p d square p dx square equals minus k square minus 1 over q d square q dy square. Now this is a constant, so it could go either side, but say this will be just depends on y and this depends on x, function of x, and this is a function of just y. That means this should be equal to some constant. So I'm going to write this as minus, let's just use an alpha square. And why do we use minus here? Because with p, I'm going to get a oscillation along the x-axis. So if this is minus plus, then it's going to be not oscillation. So make this, so get two equations, one with that and another with that. So first one, I get d square p dx square equals minus alpha square p, and you can see the p of x will be some a cosine alpha x plus b sine alpha x, just as before. It's a simple harmonic motion. And the other one looks like minus k square 1 over q d square q dy square equals minus alpha square. And this, you can rearrange it to actually look like a simple harmonic motion too. So let's see this side, and this side, this side. So that's just going to be 1 over q d square q dy square equals minus k square plus alpha square, which can be minus k square minus alpha square. So d square q dy square just becomes minus k square minus alpha square q. So if k square is bigger than alpha square, then it's going to be oscillatory solution. Otherwise, not be oscillatory solution. So this q of y will be some c cosine, let's call this beta square, is k square minus alpha square. So beta y plus d sine beta y. So beta is square root of k square minus alpha square. Okay, now let's put all the solution together. So you have psi x y t is along the x I have a cosine alpha x plus b sine alpha x, and then along y I have c cosine beta y plus d sine beta y, and then along t I got maybe e cosine kv t plus f sine kvt. Okay, so we have all of these, and they have to satisfy boundary condition. So when we satisfy boundary condition, this is not important for boundary condition. The boundary condition are here. So we want psi 0 y t equal to 0, so along the y-axis. So this is boundary condition number 3. If you do this, you can see that I'll get a times this guy times this guy equal to 0. That means a is 0. And if I try to do 1 psi x 0 t equal to 0, then y equal to 0, now we have a c, so I'm going to get b sine alpha x, and then I'm going to get a c, and then the time part, t part, equal to 0. That means c equal to 0. So 1 and 3 means psi of x, y, t is some constant. So I have a b and c. Let's make it a b together. B and d sine alpha x sine beta y, and we can just over here, that's the time part, which we can leave it alone. Alright, so I have this, and it just satisfies 2 of them. I want to satisfy say boundary condition number 2 means psi, boundary condition number 2 was psi x, y equals to b, t equal to 0. That makes it a something all the way this guys, and sine beta b, and this t part equal to 0. That means this we have sine of beta b equal to 0. That means beta, which is this guy, beta can't have just anything. Beta is required to be n pi, and n can't be 0, because 0 then the whole thing is 0. So and plus or minus will be corresponding to the same mode. So n equals to 1, 2, 3, etc. So we can say beta n equals to n pi over b. So if we go in here, you can see that beta n square equals k square minus alpha square. But alpha we may have more in it here, right? So let's look at what the alpha will do. So we satisfy boundary 2 and this, and we have one more boundary condition that will also put restriction on alpha independently of what's on beta. So one more page coming up. So satisfying boundary condition number 4. Boundary condition number 4 was psi of x equal to a, y t equal to 0. And so we have a BD sine alpha a, and then we have for the y, for the t, y part, t part equal to 0, and that means sine alpha equal to 0, sine alpha a equal to 0. Well, that means alpha a is m pi, and m can't be 0, m is 1, 2, 3. I need to have different symbol here from n, since this is independent of condition on beta. So we see the alpha, we can say alpha m is m pi over a. So going back, so we have a beta n is n pi over b, and alpha m is m pi over a, and n equals 1, 2, 3, and m equals to independently 1, 2, 3, etc. So if I have a and relationship between them is beta n square equals to k square, beta square equals to k square minus alpha square. So different beta will go with different alpha to give me different k's. Well, so we can have k mn square. You can see I will have some of these guys. Alpha n square plus beta m square. So the k actually has two indicators, two indices for this. As you know, that if I were to put everything in this equation, the original equation, I will say this guy will give me k square, and this guy will give me omega square. So the omega, so there is still a relationship omega square equals to k square v square. That means omega also have two indices. M n square is k m n square v square. So we have our modes now. We have psi m n. So each mode is indexed by two indices, and they have these values to choose from. X, y, t. It's going to be some constant here. Let's call it some amplitude. mn for that mode, and then I have a sine of alpha mx times sine of beta ny times we can have a something cosine, which is make it cosine of omega m nt plus phi mn. So we these are the mode functions, and these are the properties where alpha, beta are related like that. So this is the solution. What do they look like? So there are in the book there are some plots that have been shown. So I'll just show you. If I look at m equals to 1 and n equals to 1, they there's a hump like that. And if m equals to 1 and n equals to 2, so along the y-axis it's there's this is positive and the other was negative, and so it's symmetric to that. And over here, both of them 2, then you have a plus side and plus side. So these are, you can see the faces are this is dipped away, bumped. So you can draw them out. So this 1, we just say I've got plus face. And 1, 2, we say along the y-axis you're gonna have, if this is plus, and so there's a node here. So this is the y direction, this is the x direction. And then you can draw 2, 1 will be plus here, minus here. This is x direction, this is the y direction. X, y. And the other one looks like I have a plus, minus. So there's a a node here, node here. So you may want to play around with this. So right, that's it for this week. See you next week.